Welcome to part 2 of our lecture on astrobiology. Astrobiology is the study of and the search for life on other worlds and life in the universe. So what we're talking about here is ET, or extraterrestrial life. And this is perhaps one of the greatest questions of all in science. Are we alone? Or is there other life in the universe? So there are some questions here which we're trying to answer. Could life originate on another world? Remember from part 1, the Miller experiment showed us that organic materials that are necessary to create life are very commonly made. And so if the conditions are right on a planet, the planet should be rich with organic materials needed to start and sustain life. Question number 2, will life always evolve towards intelligence? Well, if intelligence favors one species over another, as it did for human beings, then probably yes. Number 3, where could ET life be found and how common could ET life be? Well, these are some of the questions that we'll try to answer in the remaining part of this video. Unfortunately, the only life that we know about is life here on Earth, so we're very limited in defining and even being able to characterize what is life actually. So based on what we know from life on Earth, here are some requirements that we know. Life here, at least, requires liquid water, or perhaps some other solvent could be used in place of liquid water. Life on Earth certainly requires organic molecules that are carbon, oxygen, nitrogen, hydrogen, phosphorus, and sulfur based. Moderate temperatures are required to keep water liquid and also to activate complex chemical reactions, but it can't be too hot to disintegrate organic compounds. And the other factor that we know that's necessary is time. It took several billions of years on Earth for life to evolve from simple forms into more complex forms. So we are going to need to look for stable environments like our planet Earth was, that last for billions of years. Before we talk about searching for life around other stars, what about life in our solar system beyond Earth? Well, perhaps the best place to look for life would be Mars. Remember that evidence tells us that Mars was once a warm, wet world. There still may be subsurface liquid water today underneath the surface of Mars. Right now, Mars, remember, is extremely cold and dry on the surface, but underneath, that may be very different. So did life originate and evolve there on Mars? Could there still be life underground the surface of Mars? These are questions that are certainly going to be investigated with our future robotic rover missions to the planet Mars. Another interesting place to look for life in our solar system is not on the planets of Jupiter and Saturn, but on their moons. Jupiter's moons, Callisto and Europa, both have liquid water oceans beneath their icy surfaces. This is a image here of Europa, and what we're seeing here is basically an icy crust, but underneath this ice we're pretty sure there is liquid water. Saturn's moon Titan has a thick atmosphere and lakes of liquid ethane, and we don't know what's underneath the surface of Saturn's moon Titan. And both planets have geologically active moons with volcanoes and geysers indicating warm subsurface temperatures. And so where there are warm temperatures, there could be liquid water. So these moons of Jupiter and Saturn are going to be explored in the future for the existence of life. Let's now turn to life around other stars, other planetary systems. We know that evolution, at least here on Earth, requires billions of years. So we only want to consider those types of stars that live for billions of years. Remember that the most massive stars, the type O and type A type star, spectral class stars, for example, only live a few millions of years. So it wouldn't be a good idea to try to look for life on planets around those stars because they basically blow themselves up too early. So we're going to consider sun-like stars. Typically, remember our sun is a type G star. So spectral class F, G, K, and M stars are very common in the universe. And these all last long. They last for billions of years. We also would want to look at regions around these stars where there are moderate temperatures. So this is the so-called life zone or habitable zone around a star. So for example, if we take our sun, there's a region close to the sun where it's too hot. So if we think about where Mercury is orbiting, definitely very slim prospects for life there. But once we get out to the orbits of Earth and Mars, for example, we're in a region of the solar system where temperatures are moderate and we can have liquid water. Once we go beyond outside the life zone, it's too cold. And now there are moons of the other planets that perhaps have internal temperatures that are warm enough, but any other planets out here would certainly be very cold, frozen worlds. So our search is basically going to be inside of the life zone of a star that is something sun-like. So for example, type F stars, there are about 6 billion of these in our Milky Way. Type G stars, these are like our sun. There are something like 15 billion of these. Type K stars, 24 billion, and the most popular or common star is the small M-type star. There are something like 150 billion of these in our galaxy. Notice that as the star gets smaller and smaller and smaller, the life zone gets closer and closer to the star. We talked about earlier in this course the discovery of over 4,000 exoplanets or extrasolar planets that have been discovered in our Milky Way galaxy. And we're just beginning this hunt for extrasolar planets. And remember also, we're limited by our technology. This is a diagram showing our Milky Way. Here's where we live here. This is the location of our sun. We're only able to search for planets in this tiny little region nearby our sun. We don't have technology yet to look elsewhere in our galaxy. But even in this little tiny region right here, we've already found more than 4,000 planets. I showed you this slide earlier in the course. This is a list of about 30 possible Earth-like planets that orbit in their star's life zone. So these are relatively small planets. Here's for scale. This is our Earth over here. And so we think that these planets are probably terrestrial-like, meaning they have rocky crusts and perhaps atmospheres like we have on Earth. And all of these planets exist and orbit inside of the life zone of their stars. So the temperatures could potentially be moderate enough to sustain liquid water. So these would be high, candidates for future exploration and study for extrasolar life. How many Earth-like worlds are there in our galaxy? Well, we don't know the answer to this, but we can kind of make a rough estimate based on doing surveys and taking samples of planets. So remember the Kepler space mission, which found thousands of planets. We're able to apply statistical methods to that data, and based on that, astronomers have declared there may be as many as 40 billion Earth-sized planets orbiting in the habitable zones or life zones of Milky Way stars. So this is just in our galaxy alone. So imagine 40 billion Earth-like planets. So this is, these numbers like this give us more hope and confidence that there could be life elsewhere in our galaxy. So how can we find or prove that there's life somewhere else in the galaxy? We can't send space probes to other planets, unfortunately. They're just too far away, and it would take tens of thousands of years for our space probes to even reach one of these planets. So instead, there are some other methods, and one of them is called SETI, which stands for the Search for Extraterrestrial Intelligence. SETI is basically a project using mostly radio telescopes, and when they're used to listen for intelligent messages from extraterrestrial civilizations. So the idea here is that if another technological civilization like our own was using radio technology, then some of these radio waves would escape into space. For example, on Earth, ever since radio was invented here over 100 years ago, we have been sending radio waves, TV waves, radar waves, etc., out into space. They just leak away from the Earth, almost like interference. And these radio waves are traveling away from the Earth at the speed of light. So by now, other intelligent civilizations may have even picked up our radio emissions. So the idea is if they could hear us, then perhaps we could hear them too. So there has been, for the last several decades, an ongoing search using radio telescopes to basically listen into the stars and try to see if we can pick up messages from extraterrestrial highly advanced civilizations like ourselves. And of course, so far, we have not found anything, but we're just beginning this type of search. So how many of these advanced technological civilizations might be out there in our galaxy? Well, again, this is something we certainly don't know for sure, but we can try to do a rough estimate. And this was first done by the astronomer Frank Drake, and his results are what is called the Drake equation, which is shown here. This is Mr. Drake here. By the way, you don't have to know details of the Drake equation, and you won't have to do any of the math, but you may be asked to know what the purpose of the Drake equation is, and that's what we're going to talk about next. So the Drake equation estimates the number of advanced extraterrestrial civilizations in the Milky Way galaxy by combining several statistical factors. So the number of technologically advanced civilizations like ourselves is n over here on the left, and n is the product of a bunch of different factors. Some of these factors we know pretty well, and others we don't know well at all, and so it's a combination of factors. For example, the rate of star formation in our galaxy, well, that's something that astronomers know. The fraction of those stars that have planetary systems. Up until recently, this was not known, but now we tend to think that the vast majority of stars have planets based on what we've seen out there with our telescopes. The number of planets that are suitably that have a suitable environment for life, that's this factor here. The fraction of planets where life actually begins. Well, now we're starting to get into more and more sort of sketchy parameters where we don't really have confidence in the numbers. So all we can do here is make sort of some wild guesses. We can make optimistic guesses or pessimistic guesses and see how the numbers come out. Interestingly, the last factor here, which may be one of the most important, is L, and this is the longevity or the length of time that a technologically advanced civilization survives. If we think about ourselves on Earth, we've only had technology in terms of advanced technology, such as electronics and nuclear power. We've only had this for the last roughly 100 years. And during those 100 years, you can see that we've basically developed the ability to extinguish ourselves. We could blow up our entire planet and human population several times over by using all of the nuclear warheads that are in stock. So that's kind of a pessimistic look at the human race. But the idea here is that if the human race wipes itself out in a short amount of time, then it's very less likely that we'll ever be detected. So the longer a civilization lasts, the better chance we have of finding it. And so that's what this factor L is here. So by putting together our best guesses for all of these factors here, and remember, most of the factors are highly uncertain, we come up with a number of about 10,000 civilizations in our galaxy. So if that's true, that means in our Milky Way galaxy alone, there may be 10,000 highly advanced technological civilizations like humans in the galaxy. But think about the numbers, though. This is only one civilization out of every 20 million stars, because there are something like 200 billion stars in our galaxy. So finding one civilization, you might have to look at 20 million stars. So this is like finding a needle in a haystack. Some final thoughts on this chapter and our whole course here on astronomy in general. We showed in the last slide, using the Drake equation, that we think that intelligent life may be very common in the universe. But someone, Enrico Fermi, famously asked, well, if intelligent life is so common, where are they? Why haven't they shown up? Why haven't they contacted us? And that's sort of an interesting question in itself. There are obviously two outcomes to this question. You know, are we alone or not? So what if we are alone? What if we're the only life, or at least maybe the only intelligent life in the entire universe? Then we would be privileged to be the only intelligence in the entire universe, and our existence is more precious than ever. But more likely, at least I think, what if there are others? What if we're not alone? Then our self-centered isolation of humanity would have to be reevaluated. We would share the universe with others. Humans would be part of a cosmic community. I'll finish off our lecture here in our course with a famous quote from the famous astronomer Carl Sagan. He said, "The universe is a pretty big place. If it's just us, it seems like an awful waste of space." Thank you very much, and have a great day.